Okay, so this talk is about the quantum simulator deep dive. We have Dr. Guerreschi and Dr. Helena Liebelt giving the seminar. So please, you have the floor.
Thank you, Enrico, for the introduction. Can you see my screen and hear my voice? Okay, that's great. So first of all, thanks for having us. Thanks for the invite. Today, I'm gonna give all the full presentation. Helena is also here connected, and I'm gonna talk about Intel Quantum Simulator. A bit differently from some other talks from the industry players in which a roadmap is presented. Here, we wanted to give a bit more technical information about really how the quantum simulator works under the hood. Okay. So the presentation is divided in two parts. The first one is short, is substantially a quick introduction to quantum computation, just to mention a couple of concepts that we will use during the talk. And the second part, we will ask why we need a quantum simulator and try to clearly answer this question. The second part of the talk instead will be about the Intel Quantum Simulator itself. And so we will discuss a few aspects of how we represent the states, how we represent an operation on the states, and then a few other features that we would like to highlight. So, sorry, let me maybe start also count a time for the presentation so that I know how we are doing. Okay. Quantum computation. In a nutshell, quantum computation is a new way to store and manipulate information. And the hope is that having access to a different kind of operation that we call gates, we also brings to a different algorithms that has a different scalings compared to their classical counterparts. The hope is really that in the scaling behavior, quantum algorithms are faster than or requires less steps or computation than classical algorithms. Now, typically one can look at an operation acting on multiple qubits. But a nice property of quantum computation is that every of these operations can be decomposed into the action of a 1 and 2 qubit gates only. And in particular, this is just a point for the talk, a single kind of 2 qubit gates is sufficient to achieve universal quantum computation. So the scope then of the simulator will be to be able to prepare a state, so initialize the states, to apply 1 and 2 qubit operations and then measure the states and extract information. Now, how can one visualize quantum algorithms? Typically, they are shown on the left like a sequence of quantum assembly instructions or QASM instructions. Otherwise, on the right, they can be visualized as a quantum circuit. I think that I don't have to enter details on the explanations. Now, the question is, why do we need a quantum simulator? And there are at least two practical reasons why we want a quantum simulator. The first one is like we want to understand the performance of quantum algorithms. And in the early age of quantum computation, algorithms came with a sort of performance guarantee. Things in terms of a Grover's search algorithm or the Shor algorithm for factorization. They provide an expected number of operations that are required before achieving solution. In the recent years, instead, things change a bit, and quantum heuristics algorithms are now entering kind of the field. And with these heuristics, we don't really know what is the quality of the solution that we achieve, and we don't really know the number of operations required to achieve such solution. So I think it's particularly important to have a simulator to kind of address the performance of these algorithms. The second point is that having a quantum simulator together with a realistic noise model will allow us to characterize the noise sources in the devices that we are building. And this characterization should go beyond just a qualitative understanding of the noise, but really move towards a more quantitative understanding. There is also a third reason that this is more for this high-performance community or high-performance computing community, that is really like the simulation of quantum systems is one of the tasks that very naturally extend to the exascale. So now that the exascale machines are coming up, then simulation of quantum system is one of the very natural applications. On the other side, you may have followed the news that about 1 year ago, Google claimed the achievement of quantum supremacy. So what does it mean, quantum supremacy? In a kind of also here in a nutshell, is that Google was able to perform on a quantum device a task that is impossible to perform in a reasonable time in any possible classical system. This also means that the device that they had is not simulatable, right? Because if you could simulate, then you can also reproduce the same task. So are we in an era in which quantum devices are already beyond simulation? So is there still a values for the quantum simulator? And and yes, I believe that there is, and I tell you why. For both points, for me, are still very valid. The first point is that there is kind of a knob in a simulator that you can turn and decide what is the level of noise. And actually, for the approach that we are following, the simulation of an ideal system, so a noiseless system, actually takes the least amount of computational time. So that we can even think in terms of a simulator just being able to simulate high quality qubits or even error corrected qubits, something that at the moment will require, from a physical device, a large overhead. From the second point of characterize the quantum devices, I believe that being able to simulate 30 or 40 qubits also with noise will help us a lot to understand long range errors or interaction between the qubits. And so I believe that both applications are here to stay. There is a small teaser that I want to add. If one look in the very long terms, how to characterize a quantum devices, when we want to characterize larger and larger modules of this device, we are proposing, together with some colleagues from Toronto and Harvard, a quantum computer aided design. So the idea that we could use a quantum computer and quantum algorithms to try help designing the new generation of quantum chips. But this is not the content of today's talk. The content of today's talk is really Interquantum Simulator. And Interquantum Simulator has been released open source. We changed the repository about 1 year ago, so I just want to remind the people the link. So not everybody has adjusted. So please, in case if you intend to use, just explore the repository. You can ask a question, you can develop even and contribute. So we are very open. Let me see, sorry, I'm just reducing my picture to read better. There are multiple features, some features that I think that came from moving from what felt like a research project a few years ago to what is really a more mature open source project. Part of this transition was clearly creating a more robust building process that doesn't require, really much of the understanding of how it works. It's based on CMake, it's customizable. We extended the tutorial, the examples, but there is also a Python binding. So the Interquantum Simulator also builds as a Python library. Now we see Python that is kind of dominating language into the quantum computing frameworks. So in this way, you can very easily use Quantum Simulator, Interquantum Simulator in Python. For example, we have multiple Jupyter notebook as examples. The core, however, of Interquantum Simulator is really being able to leverage all the computational boost coming from high-performance computing environments. So it's a parallel and distributed implementation. And it's this implementation that will be the focus of the next part of the talk. So first of all, let me set a bit the stage. What do I have in mind when we speak about this high-performance computing environment? We consider a network of computing nodes, all right? And in which every node has its own processing power, CPUs, but has also its own local memory. And there is a high bandwidth interconnections between the different nodes. The first part to understand the simulator is really thinking how the simulator represents quantum states inside of it. So a state of n qubits is typically represented as a vector of 2 to the n complex elements, okay, or complex amplitudes, how we call it. And this makes it clear that the memory cost grows exponentially. You just add 1 qubits and you double the space. You arrive at a certain point very quickly in a way that you exhaust the local memory available in your node. So how we are able to simulate more qubits? The idea is kind of simple. You just divide the states into different parts, and then you separate the parts and store each part of the state vector into different nodes or processor in this case. If we have 2 to the p processors, we will have that every local memory has size 2 to the m, when m is equal to the number of qubits n minus p. Now, why I'm stressing out this p, m, etc.? Because given n qubits and this configuration, we will say that the first m qubits are local and the remaining p qubits are global. What do we mean? We call substantially a local qubits a qubits for which, if we have to simulate a gate on these local qubits, we do not need communication in the simulator. Let's look at how it works. We have a state here. It's an example of a 3-qubit state. So it has 8 amplitudes from indexing from 0 to 7 in binary notation. And let's imagine that we have 2 processors. So we have 2 memory spaces, memory space 0 and 1. In this case, we have 3 qubits. 2 of them, the one or low index, will be local qubits, and 1 of them will be a global qubits. What does it mean, apply a 1-qubit operations? A 1-qubit operation can be seen as a 2 times 2 matrix. It's here visualized at the bottom. And then this matrix, if you want, you can apply a tensor product with identities to really creating it representing as a matrix on the full states. But I think the idea is, like, if we apply this gate U on the qubit K, the amplitudes are actually updated in pair, okay, as is shown in the right side, in which we select 2 amplitudes that have the same index in binary notation apart from index K. The same, let's say, the bit K is the same as the index of the qubits we are acting upon. How do we visualize this action in amplitudes, right? I'm showing 3 different patterns of this amplitude pairing, coming from the application of a gate on qubit 0 on the left, on qubit 1 and qubit 2. What we can see is that for acting on the local qubit 0 and 1, these amplitudes that needs to be updated together are actually paired by this red dot line, and none of these lines cross the memory boundary. This means that the amplitudes can be updated without the need of communication. This is different from what happened for the global qubits, in which actually all these pairs are stored in different nodes. In this, to be able to perform the simulation, we then need communication. The kind of the reference provides is the first publication about the interquantum simulator, and provide the communication pattern from MPI. Here we also said that is required to perform not only 1-qubit operations, but 2-qubit gates as well. And interquantum simulator allows the application of 2 kinds of gates. One is the control gate, so in addition to arbitrary 1-qubit gates. So you can apply control gates of the form on the top, or swap type gates that is of the form of the bottom. Either of the 2 is sufficient to achieve universal quantum computation, so we can simulate every circuit. But what is the beauty of this form of gates? If you kind of give a look at the matrix form, there is never more than 2 non-zero elements per row or column. And so this also means that the amplitudes, when we want to simulate this, are updated at most in pairs. And so we can use the same concept that we discussed for the 1-qubit case, and we obtain similar results about if you apply the gates on local qubits, you don't need communication. Quantum simulator, the interquantum simulator is a distributed code, right? And so one of the questions in high performance computing is immediately try to address how well does it scale to more computing nodes. If I have, in particular here, I'm presenting the strong scaling study. The strong scaling is I fix the problem, and then I assign more and more classical resources to solve it. And the idea is like, how does the computational cost scale, right? The best hope scenario is like if I double the number of computational resources, the time will halve. So let's look at what exactly we are plotting here on the left. I don't know if you can see my mouse, but let's focus on the blue curve, that is the one at the top. We are reporting the time that is taken to simulate a 1-qubit gate while we are swapping the qubit index, okay? You will see that at the beginning, the cost of applying these 1-qubit gates stay constant. This is what happened when we apply, when we want to simulate a gate on a local qubits. But if you see, in the last 5 qubits, we have to pay a high price. This is why there is this jump in the cost of the on the time of the simulation, because now the communication overheads kicks in. The blue line, in fact, has 32 processes. 32 is 2 to the 5, so the last 5 qubits are global. Now, this is not the scaling study, right? The scaling study is like, okay, now we have 64 processes, so the orange line, or we double again, we have 128 processes, the green line. And so how does the time scales? This is a log plot, and so you can really nicely say that every time we double the classical, the computational resources, we actually halve the computational time. So that's a very good behavior. The only caveats is that also more computational resources we have, more qubits will be global. And so the communication overhead start kicking in for smaller and smaller number of the qubit index. I am left about, I believe, like 6 minutes before the question kicks in. So I would like to discuss a couple of selected aspects of interquantum simulator. And I would like to start from what we call the pool of state functionality. That is something quite unique, I think, to interquantum simulator. So this is a functionality that the idea is like it will allow the simulation in parallel of multiple circuits. So let's look at the use cases. This is kind of these 3 plots, starting from the left. The left one is what we thought at the beginning as the original use case for interquantum simulator. We wanted to simulate as large of a state as possible. And so we wanted to chop the states into as many pieces as possible to fit in a local memory. And this is what is shown on the left, that all the processors and all their local memory is used to store and process a single quantum state, and so a single circuit. If we move towards the right, we can see actually that we can divide the processors into groups, and each group of processor can actually deal with a simulation of one and only one state or circuit. And if we move even further, we could go to the case in which we use a single processor to actually simulate multiple circuits. Now, clearly, going from left to right makes that the number of qubits per circuit is reduced. But we can enhance a lot of the parallelisms, and this is taken care inside the interquantum simulator itself. There are 2 use cases that we find very natural for this pool of states feature. The first one relates to the very famous now class of variational quantum algorithms, in which substantially we can dedicate each of the different instance or circuits to running one of the variational algorithms with a very specific selection of the parameters. The second use case is actually when we want to simulate noise and decoherence. This is what I would like to expand a bit more on. So if we simulate, interquantum simulator is a pure state simulator, right? So in general, it will not include noise. And we can see from on the left side of the slides, the pure state is a vector for n qubit as dimension 2 to the n. And the simulation will be substantially we are simulating a circuit here captured by the unitary U, that is a multi-qubit unitary. And we have a state at the beginning and a pure state at the end. What happens if we introduce noise? When we introduce noise, actually we need a different kind of object to store the quantum information that is called density matrix. And so the density matrix is now a 2 to the n times 2 to the n matrix that takes quadratically more memory than just a pure state. So quadratically more memory in terms of qubits means that with the same total memory available, we are able to store only half of the qubits. This is kind of a steep price to pay, but there is a way to go around it. So at the bottom, we can see exactly what will be the simulation. You start from a pure states, right? You start with something without noise. You apply, this is kind of a noisy version of the circuits, this kind of U, and you obtain a density matrix in output. But there is some theorem that relates the density matrix in output to a sort of average over multiple realization of perturbed version of the circuits U. What do I mean? I take my noiseless circuit U, and then I perturb it in a stochastic way by adding extra gates or by kind of mimicking the mistakes or the error that can happen. And this will give rise to these circuits UK. Now, UK is just an index to mean that is generated according to a certain distribution probability of perturbed circuits. Then I need to average over multiple realization of these perturbed circuits. And if I average over a large enough number of circuits, I will actually reproduce exactly the noisy case. So how do we use it? Once we reproduce the noisy density matrix, we can also compute expectation values of observable. That is typically what one cares about at the output of a quantum computation. So the question here is really how many perturbed states can we sum? And on the right side, we can show how does, let's say, the expectation values of an observable converge the more perturbed circuits we are averaging. On the top, it can be seen that if we average around 100 circuits, we actually converge in this case. But there are cases, like at the bottom, in which we have to average maybe thousands of circuits. Now, this is exactly when the pool of states helps. We can divide this 1,000, for example, perturbed circuits that we want to to average to obtain the noisy results over the different processors, right? And so we can perform them not sequentially, but in parallel. And so we can speed up the computation simply linearly in the number of classical resources available. Let me flash slides with a couple of more features of interquantum simulator that I want to highlight. One was the Python library, right? And we are releasing very soon a new kind of update in which we are actually also using MPI environment or MPI communication protocols inside Python, so that one will be able not only to use Jupyter Notebook, but really perform eventually simulation at scales, writing just Python code. Some other things that I want to mention is that we have a Docker file, so it can be built also in a container space for somebody who wants to think more in terms of a container. But in this case, at the moment, there is no MPI protocol involved. So can interquantum simulator be useful to your research? If yes, please give a look to the repository. You can ask information. We are trying to be active in replying. Excuse us if we are not super fast, but there is a very great, let's say, motivation from our side. On the other side, if the simulator is not what you need for your research, maybe you can ask for adding the functionality that you need. Or even better, this is the beauty of an open source project. You can even think about developing them. And with this, there is the legal information slides. Clearly, what I talk about today is for educational purposes. Okay, nothing, not giving you any intellectual property. And then I would like to thank you all for listening to the talk, and thanks clearly to the team, to the interquantum simulator teams that helped develop the simulator, and to all the contributors in GitHub. Thanks a lot.
Thank you. Thank you for this very interesting talk. I do have a question, very technical. It's about the 2 qubits gates.
Yes.
So what kind of operations do you have in mind? Is that something implemented to emulate something which is going to be built at a physical layer, or is that something you consider prepared at the quantum error correction level as a logical qubit?
Yeah. Yes. So I would say that the distinction here is not okay. So on one side, it depends on the level of fine graining that you want for the error correcting qubits, right? I think that the application are twofold. One is really mimicking physical qubits, especially while we spoke about noise, etc. This will be a physical qubit level. When we want to speak instead and apply to, let's consider that one hipster qubit is a logical error-corrected qubits, we have to neglect then the error procedures, the error-correcting procedures. So we will not fine-grain into the specific error corrections, but we will just use the error rate that doesn't reflect the physical one, but the error-corrected one. So I would say that the most natural answer would be think more in terms of physical or abstract qubits. Yeah.
Okay.
Do you have to comment on the kind of 2 qubit gates, or?
Oh, it's okay. Yeah. So let me thank the speaker And let's move to the next speaker, which is Marta Mauri from Zapata Computing.
Hello, everybody.
Hello, nice to see you. So can you share the screen? Okay, so Marta is going to talk about quantum enhanced machine learning with near-term devices.
Great. Thank you for the introduction, and thanks to all the organizers for organizing this nice event and for inviting me to give a contribution. So I'm Marta, and I'm a quantum software engineer at Zapata Computing. And as Enrico was mentioning, I'm going to talk about quantum enhanced machine learning with near-term devices. Let me start very quickly by introducing who we are. So Zapata is a software company, a startup that spun out of Harvard in 2017. And our mission is to build software for quantum computers and develop algorithms for real business use cases, sorry. And our algorithmic efforts span across different industries, namely optimization and logistics, or statistical modeling in finance, for instance, but also materials discovery and quantum chemistry simulations. This is just to give you like an overview of what we do at Zapata. And in order to support the development and implementation of these new algorithms, we built Orchestra. This is our product. It's our platform that is a workflow-based platform that allows us to orchestrate the different frameworks, backends, and libraries and tool sets that are available today in the quantum computing domain. And today I'm going to talk a little bit about how we used Orchestra to implement, develop, and get exciting results in the domain of quantum enhanced machine learning. So let's take a closer look to the problem that we are interested in, namely the use of quantum computers in the context of generative modeling. So what is generative modeling? This is an unsupervised learning task in which the goal is to model a probability distribution of observed data and then be able to generate samples accordingly. So for instance, one could be interested in generating specific patterns, images with the specific patterns, as the one we can see here on the left. For example, there is this bar stripe data set, which is extensively used in the study of generative models, which consist of black and white images of M by M pixel that can display only either horizontal stripes or vertical bars. And this is, for example, one interesting thing, that you can be able to generate images with a certain pattern. But maybe a more appealing application that maybe most of us have seen is the ability of generating faces using generative adversarial networks. So given pictures of people, the goal is to generate new faces that resemble real people, but that are actually fake. And with this, I invite you to check out the whichfacesreal.com website, which is really impressive in terms of the performances that these generative models are able to obtain today. So in a nutshell, given samples from probability distribution, we want to be able to generate new samples from the same probability distributions. And let me stress that this task is a hard task, in the sense that even compared to other machine learning tasks, this is pretty difficult. Like with respect, for example, compared to classification kind of tasks. And how can we understand these is through this example. So you can all think how much easier it is to recognize a Van Gogh's painting rather than actually making one yourself. And so this gives an intuition, at least, of why this task can be difficult. And indeed, the classical techniques that are available today, even though they're powerful, they also struggle for many applications. And therefore, one question that arises here is whether we can use quantum models running on near-term devices to overcome this limitation, or at least to enhance the capabilities that we already have. Let me just stop for a second on why we are interested in quantum computing at all here as a powerful potential candidate for this announcement. So first of all, there are at least two intuitions. So first of all, quantum generative models are provably able to learn distributions that are out of reach from the classical perspective. So we are actually able to explore regions of the probability distribution spaces that are very difficult to reach with a classical technique. And the other motivation is that quantum algorithms are can potentially avoid some of the pitfalls that we can have in the classical approach by providing an improved training and an enhanced sampling way, let's say. And so at least these are two initial motivation that makes us hopeful that this approach could be useful. And how do we want to actually do that? So how do we want to introduce the quantum component in the classical machine learning domain in a hybrid fashion? Because we also need to take into account the severe limitations that we nowadays are there for the quantum hardware. So we want to be NISQ friendly, so near-term devices friendly, and for this reason, we introduce a hybrid paradigm in which we just substitute the classical machine learning model with a quantum machine learning model. This is one of the paradigms that are suggested, and this is the one that I'm going to present today, especially talking about these quantum circuit board machines new method. So what is a quantum circuit board machine? This is a generative model that represents a probability distribution using as a quantum state. So the idea is to approximate any arbitrary distribution in a NISQ-friendly fashion, as I was mentioning before. So we have, let's say we have a certain data set that defines a probability distribution that then we want to be able to learn and load into a quantum state for then generating samples from that quantum state that resemble the original distribution. So here you can see the distribution of the bars striped data set that I mentioned before, which is a uniform value for the probability for the bars stripes patterns and the zero probability for the other images that don't display the pattern that we are interested in. And so we want our model to be able to learn this probability distribution and exactly produce these patterns. How does the QCBM work to obtain this result? So it starts from a vector of parameters that we can initialize and use in a quantum circuit, in a parameterized quantum circuit, which then is able to transform an initial qubit state to a final output state depending on the parameters. And this final output state contains a probability distribution. So the wave function amplitudes encode a probability distribution according to Born's rule, and then measuring the quantum state in the computational basis, we are able to obtain some quantum outcomes, quantum measurements, that we can compare with the target distribution of the data set. So the idea is to estimate the mismatch between the quantum outcomes and the data, the target data that we have, and use a classical optimizer to minimize this mismatch, which is encoded into like a well-suited wave function that one, cost function that one can define. So the idea is exactly to use a classical optimizer to iteratively update the parameters of the quantum circuit and then minimizing the cost and getting to a final result that is able to represent the probability distribution that we are interested in. And this is therefore is an inherently hybrid architecture because we have a parameterized quantum circuit that is meant to be run on the hardware. Sorry, on the quantum hardware, on the QPU, whereas the classical optimizer is an entirely classical CPU kind of task. So there are a lot of components that are involved in this problem, in this algorithm. So one thing that I want to mention is the fact that there's a first step in which you need to map your data set to qubits. And in this case, we have 2x2 images, which are black and white. So it's kind of straightforward to map 1 qubit to 1 pixel. But there are other cases in which this is less easy, and it's part of the, it's actually like a big part of the development of the algorithm. But other things that can be tweaked and chosen by the developers and the users are the cost function that you can define. So here we decided to use this clipped negative log likelihood, but this is not the only choice, absolutely. And also the classical optimizer, there's a variety of optimizers available, obviously either gradient based or gradient free, evolutionary strategies, like a lot of different options are available. But also on the quantum side, you can specify the initial state and you have to prepare that. You can choose what backend to use, so either a simulator or a hardware, like if you have that available. And the choice of the backend also affects the choice of the answers of your circuit, meaning how many qubits, how many, what is the connectivity that you can use between the different qubits, which gates are the best to use. And then there are also a lot of other different things that you can choose in the quantum model, like noise models and error mitigations, these kind of things. So there are a lot of different components. In our case, we decided to use this type of ansatz that considers layers of single qubit rotations and then XX entangling gates, which are ion trap native gates. And this is going to be clear in the following why we chose these gates. And the point is that if we try to orchestrate all of these components using our platform, we are able to actually train our model to be able to get the target distribution learned, and therefore to be able to generate the patterns that we are interested in. Here in the training, you can see that the cost function gets minimized and gets closer and closer to the expected value, as well as the final, the target the measured distribution from our quantum state gets closer to the target. And this is also shown by the fact that we highlight the patterns that we are generating that we can sample from our quantum state here on the right, and we see that they are mostly the ones that we are interested in, with the bars and the stripes, and all the way to the end where the distribution is even more stabilized. So we were able to train our model to reproduce this bars and stripe distribution. This is like promising method, but one of the challenges now in this approach of quantum machine learning is actually how do we scale to larger data sets? That is, this problem is relevant for business applications, but at the same time, it's a big challenge, not the only one about this framework. And it is a big challenge because, as you can, maybe we can have an intuition of that with thinking about the qubit mapping that I mentioned before. So if we map one single pixel of an image to a single qubit, we can easily understand that as we want to consider larger images, then this becomes like soon impossible and unfeasible if we have this mapping with these devices. So we need a new strategy to get we need a strategy to be able to deal with larger data sets. So how do we address this challenge to scale up to larger data set? So first of all, let me tell you like a couple of data sets that could be interesting for our use cases. One is the handwritten digits data set. So the so-called MNIST data set is very widely used in machine learning. So it contains images of handwritten digits and black and white. And then there are also other data sets that can be interesting that may come from real data, especially in the financial domain. So for example, distribution of prices, of stock market prices. So what is the idea that the paradigm that we are considering for our quantum machine learning model here to scale up to larger data set is, this is simply the idea of keeping the dimensionality of the quantum model low, because this is a limitation that we have from the hardware, and incorporate this model into a workflow that contains pre and post-processing classical machine learning steps that are responsible for compressing and decompressing the data. So the idea is to use our QCBM wrapped in a more complex machine learning architecture, which is classical. So let me explain what is the architecture that we use. So let's start with the generative adversarial network. I don't know if you're familiar with that, but like this architecture has different components. There's the generator, which is responsible for generating images, and it starts from sampling from this prior distribution that gives some variety from which the generator sampled to create some images, which this prior is usually chosen to be a random uniform distribution, so like just noise. And therefore, at the beginning of the training, the generator is just able to generate noise. And the task of the discriminator instead is to recognize that the images generated by generator are fake, whereas the images coming from the real dataset are actually real. And so in an adversarial game between generator and discriminator, the generator learns to generate better and better images as the training progresses. And just as a note, the generator and discriminator are both meant to be assumed to be deep networks. So this is the generative adversarial network framework, but we can enhance these going to the associative adversarial networks framework, which comes out from these observations. So if you look at the prior, we said that it's usually meant to be uniform distribution. So the generator learns how to generate images sampling from this uniform kind of space. But then if we look at the discriminator, especially in one of the latest layers, this one is called latent space and provides a compressed representation of the data, especially of their features. So when we feed real data into the discriminator, the observation is that this latent space is far from being uniform. There is a very clear structure that depends obviously on the data that we are using. And so the idea is, can we use this information about the structure of the latent space in the prior in such a way that the generator is able to sample from this space in a more efficient way and therefore to generate hopefully better data. This is the idea of the associative adversarial network, in which the prior is trained, is represented as modeled as an RBM, so a classical generative model, to learn the structure that is in the latent space, and it's trained. It's also trained during the architecture training, and since it's able to learn the structure, the result is that it can generate better data. Now, since the point here is that this latent space has a reduced dimensionality, as I was saying, is a compressed layer, therefore it's suitable for to use these for quantum enhancement in a NISQ-friendly manner, in the sense that if we have a small dimensionality, we can hope to use a quantum model which is amenable for NISQ devices to model this prior distribution. And this is exactly our proposal that we published on the arXiv last week, that is called Quantum Circuit Associative Adversarial Network, which just consists in using a QCBM, the QCBM that I described before, as the prior for the generator. And this QCBM that I described before assumed that the measurements of the quantum state are performed in the computational basis. But here we also proposed kind of an enhanced approach that we called multi-basis QCBM, in which we can exploit the unique property of the quantum state to be able to encode a probability distribution in different bases. So the idea is that we also want to measure the output state in other bases than the computational one. And so we introduced these two variants. One is the orthogonal basis QCBM, in which we also measure in the Y basis, and the trainable basis, in which these rotations that are put in front of the measurements to change the basis measurements are actually free, and they are learned during the training of the hybrid architecture. This means that this whole framework is also able to learn what is the best basis to use for getting information from your quantum state. And this is like the enhanced kind of approach of the QCBM compared to what I described before. So let me, so we, in this case, even more components are involved, as it's clear from the difficulty of this explanation of the structure. And so with Orchestra, we were able to explore the different priors that I mentioned. So a simple QCBM or different basis QCBM options, but also the classical RBM of the associative adversarial networks and the uniform classical GAN. Like easily recycling part of the code that we wrote. So it's easy to swap between this framework, and it's also easy to swap between different backends. So we are able to run this model on simulators, but also on actual real quantum hardware from IonQ. So by running this model, we were actually able to obtain the first high resolution images using a quantum computer. So let me show the results that we obtained using the Ion Trap IonQ computer. And here I'm showing as a measure of the performance, the inception score, which is a popular metric to assess performances of GANs, which measures both the quality of the output of the generated images, but also the diversity. And we can see how this inception score improves during the training for both classical simulation, so DC GAN simulation, the squares, but also for quantum simulations on simulators, so the triangles, or on the actual hardware, the hexagons. So as the training proceeds, we can see that at the beginning, there's a very blurry image that we can produce, but as the training proceeds, we can see that the generator, so the model, gets better and better at generating images all the way to the end, in which we are actually able to obtain an image of digits which resembles the data set. So with Orchestra plus the IonQ hardware, we were able to obtain a result that is really promising, in the sense that with a QCBM, we were able to get a better GAN. And far from being like a claim of quantum advantage, nonetheless, this result is a very promising result, and is a very big step forward in the context of quantum machine learning with complex and full-scale machine learning data set, as you can see here, by comparing the results that we obtained, that we just published, and the state of the art in generating high-resolution digits with a quantum computer. So this indeed is a very promising result, which for sure requires more study and more benchmarks and to assess limitations and performances, but for sure this is a very promising direction that we are excited to explore and continue to study. If you are interested in learning more about this, I invite you to check out our website, zapatacomputing.com, but also the Orchestra website with the documentation, where you can also find more information about the tutorial that I just explained about the QCBM. And with this, I would like to thank you for the attention, and happy to take any question if there is some.
Thank you. Thank you for your excellent talk. Let me see if there is any question. I do have one. It's about if you have any idea, if you have tried to compare with a generative mode of quantum annealers.
So actually, all the simulations were just on a gate-based model, in the sense that the QCBM itself is a gate-based idea.
Yeah, so you have because the kind of problem you can try to solve can be very similar. So I was wondering if you have any benchmark to compare the two methods.
No, we just focused on the gate-based approach, but for sure it could be interesting to see how these work on the deep wave or kind of quantum annealers approach. But we haven't tried. We're more focused on the challenges for the gate-based paradigm. I would say.
I see a question. Did you try introducing some noise such as introducing a pixel in the picture, and if you have how it performs.
Okay, so actually, all the simulations were, so since I showed like the state of the art before our work was like not very promising, was not very not a very good result. So we didn't try yet to add noise, because we wanted to try if we were actually able to improve these. So this is like the first step of a certainly more in-depth study that is needed, and I think it's super interesting to proceed in this direction. But this is like just like an initial step, and therefore like we didn't try with noise, but it's definitely an interesting direction to explore. But this was just, you know, like, can we actually do something interesting with this new model? Like, can this work? So this is promising, and it paves the way for additional studies for sure.
So let's thank the speaker again.